When this $10 billion device directed its infrared vision at the exoplanet K2-18b, located 120 light-years away, it detected dimethyl sulfide, a sulfur compound that on Earth is produced exclusively by living organisms. Does this mean the question is settled? Can we finally answer the oldest question of humanity, namely, whether we are really alone in the universe? The answer is not so simple, and this is exactly the heart of the astronomical debate. While some experts are already popping champagne corks, others call for a bit more patience and point out that even the capabilities of the most powerful space telescope of all time are limited. Dimethyl sulfide, DMS, probably plays no significant role in the daily lives of most people. In fact, most people have probably never heard of this particular chemical compound, even though they've most likely encountered it at one time or another. DMS is formed by microscopic algae, phytoplankton, that drift in the upper layers of the oceans, and it is responsible for the typical smell we notice when we're at the beach. In addition to its olfactory properties, DMS has another important feature. So far, we know of only biological sources for its production. When the creation of a substance requires the help of living organisms, it suggests that biology plays a very specific role in the search for extraterrestrial life. Hence, it's understandable why the astronomers at Cambridge celebrated in September 2023 after the James Webb Space Telescope detected this potential biosignature on exoplanet K2-18b. The discoverer, Nick Kamatasudan, stated that he and his colleagues were completely shocked by the readings. It is no surprise, because detecting DMS in the vastness of space is a very strong signal for extraterrestrial life. What started as a shock for the scientists quickly turned into an almost euphoric celebration, elevating the James Webb Space Telescope to the rank of key tool in cosmic life research. But is the matter as settled as it appears? If the corresponding molecule on Earth is produced only by living beings, and we discover it on an extraterrestrial body, why hasn't NASA officially announced that microscopic neighbors are lying dormant on K2-18b? The answer is because, as is often the case, the devil is in the details. Fundamentally, the conditions in the case of K2-18b are far from ideal. K2-18b is located about 120 light-years away in the constellation Leo, and it is suspected of being an oceanic planet. In other words, it may be a planet whose surface is entirely covered by water, potentially harboring life. K2-18b was first identified in 2015 thanks to the Kepler Space Telescope, and it orbits a red dwarf star, K2-18, within the habitable zone. This zone is the range of distances where a planet must be located relative to its parent star for liquid water to exist permanently. As we all know, water is essential and considered one of the fundamental pillars for the development of life similar to that on Earth. Although K2-18b is much colder than the Sun, its companion planet receives roughly the same amount of radiation as Earth due to its orbital configuration. The planet is just 0.14 astronomical units from its parent star, completing an orbit in just 33 days. Indeed, the list of potential biosignature gases includes methane and carbon dioxide, suggesting that K2-18b could be a habitable planet. If this is truly the case, it would be a cosmic breakthrough, as to date, such aquatic worlds only exist in theory. The large amounts of methane and carbon dioxide detected, combined with the absence of ammonia, suggest that K2-18b is a planet similar to Neptune, covered in liquid. However, the substances detected also present a complex problem. They make the correct interpretation of the data more difficult. The DMS mystery, in principle, the DMS signal was prominently pronounced in the data sets collected and only revealed itself after the data were analyzed in a very specific way. The fact that the DMS signature identified by Webb's near-infrared spectrograph, NIRSpec, appears in a spectral range of 3.4 microns, which overlaps with that of methane, has complicated matters. The scientists believe that distinguishing between DMS and methane is currently beyond the capabilities of NIRSpec. Does this mean that the capabilities of Webb have already been fully exhausted and that we won't be able to uncover the true nature of the DMS question? Fortunately, no. Researchers emphasize that unequivocal proof is still conceivable in principle. DMS and its decomposition products also generate a signature in the mid-infrared range between 9 and 13 microns, and coincidentally, This is exactly the range in which Webb's MIRI spectrometer operates. While NASA's initial announcement spoke of a potential detection of dimethyl sulfide, the Cambridge scientists, led by Nitka Madhusudan, wanted to know more. So, astronomers once again used Webb's sharp infrared vision to unravel the mystery surrounding the supposed biosignature. To do so, the scientists planned 8 hours of targeted research for DMS detection. 1 or 2 days later, the research team should receive the data and begin the evaluation. However, it's in the nature of things that such an evaluation of the data is, to say the least, laborious, meaning it can take months before it's fully completed. The good news is that researchers have been working on the analysis for more than 6 months, and it won't be long before the latest findings on the presence of DMS on K2-18b are published. So when can we detect DMS? Fortunately, the rest of the astronomical community is not left to wait idly by. They can also approach the question of DMS from a theoretical point of view. Using their models, scientists can check when we might detect the presence of DMS on K2-18b, and that's exactly what the team led by Chongmin AI from the University of California, Riverside has done. The researchers reconstructed K2-18b's possible biochemistry using several models simulating the ocean and atmosphere that cover the planet. They then analyzed the amount of DMS that extraterrestrial microorganisms would need to produce in order to accumulate in the atmosphere in detectable amounts, and how quickly it would decompose again under radiation. The study concludes with the exciting result that the current data evaluation by the colleagues is not in vain. It is theoretically conceivable that biogenic sulfur gases on oceanic worlds rich in hydrogen, like K2-18b, could accumulate in detectable concentrations. However, as often happens, the tremendous difficulty arises here because this only applies if the organisms on K2-18b are real powerhouses. The extraterrestrial production of DMS would need to exceed that of Earth by a factor of 20 for us to be able to register it with our instruments. This is simply because most of the DMS is immediately decomposed by photochemical processes under the influence of solar radiation. In the case of much higher concentrations, which is conceivable on hypothetical oceanic planets, a natural protective effect could occur, balancing out the loss. DMS and its degradation products, such as dimethyl disulfide and methanethiol, form a kind of protective shield around the lower atmospheric regions, which are also protected from any further degradation of DMS. However, only time will tell to what extent this scenario reflects reality. What is already clear, however, is that the unequivocal confirmation of the presence of DMS would be nothing less than an unprecedented step in the history of space exploration. Although Nitka Madhusudan is currently busy evaluating the new sets of data, as mentioned earlier, he emphasizes that a single direct detection would be enough to revolutionize the entire history of science. No wonder, after all, humanity has been wondering for millennia whether there are other forms of life in space. In the end, just one example would put an end, all at once, to millennia of speculation. We cannot yet say with absolute certainty whether the breakthrough in the search for extraterrestrial life will come from C-18b, but as of now, we don't know of any other candidate that offers such a promising lead in our search for life in space. And now your search for the video leads you directly to the subscription button. Don't hesitate to click your thumb and subscribe so you never miss a new video from us. See you soon. See.